Welcome to the course module of speech signal processing, and in this video we are going to learn about the linear prediction concept, and later on this linear prediction concept we are going to use for speech signal processing. So let's begin this discussion, what we mean to say linear prediction. So now let's try to consider this speech sequence Sn, and here we have the speech sequence which is having certain number of samples, and here I have marked this sample index here, like sample number 1, 2, 3. Here I have marked it as the nth sample. The sample before this nth sample is n minus 1 sample. Similarly, the sample next to this n will be n plus 1 sample, and so on. So here now try to answer one question. Is it possible to predict this nth sample by having the certain linear combination of the past samples? Okay, is it possible or not? Okay, so what I'm trying to say is that is it possible to predict this sample number 4? Let us suppose this is my sample number 4. So is it possible to predict this particular sample number 4 by using the linear combination of this past 3 samples? Okay, is it possible or not? Okay, so if it is possible, in that case, it is possible also to predict this value. Okay, means I mean to say, if you able to show that this particular sample is having a certain linear dependence on this past samples, then we can use the concept of linear prediction to predict any samples. Okay, so any present samples can be predicted by having the linear combination of its past samples. So here you can see what we mean to say this linear prediction. So this present sample of a discrete sequence Sn can be predicted based on the linear combination of past samples, right? So here, suppose if you wish to predict this nth sample by using past 3 samples, okay, let us suppose, right? So if you consider only the past 3 samples, in that case, I will say that the prediction order is 3. Okay, so because we are just choosing last 3 samples to predict the present samples. In a similar way, we can also do that. We can use the past 5 samples, right? So if you use this number of past sample is equals to 5, in that case, the order of prediction, we are going to say that it will be 5. Okay. So here you can use any number of samples to predict the present sample. So basically the number of past samples that we are going to use to predict the present sample is normally called the order of prediction, right? So in such cases, the signal that we are going to predict will be represented by this S cap n, right? So let's try to understand the same concept by a simple example. Okay. So let us suppose we are having a space sequence Sn in which the samples which is available is 0.5, 1, 0.75, 0.6, and 0.5. So now I will show you that if you see this sample number 0.75, it has certain linear dependence on this past two samples. Okay, so it is having certain linear dependence that we can show here. Okay, so the meaning is that this 0.75 can be generated by writing a certain linear equations. Okay, and providing a certain coefficients of that particular linear equation such that the combination will give you 0.75. So how to get those values of coefficients you can see here. So let us suppose the coefficients are A1 and A2. Then A1 multiplied with 0.5 plus A2 multiplied with 1 should be equals to 0.75. So let's try to understand. If we consider A1 equals to 1, let us suppose we are assuming this, then you can easily get this A2 value equals to 0.25. Similarly, if you assume A2 equals to 1, in that case, A1 will be equals to minus 0.5. So here I have just shown you the two combinations, okay? A1 and A2's only the two combinations, the possible combinations that are going to give you this sample 0.75, okay? So there are other combinations which are also possible, okay? So I have just shown you only two combinations, right? So there could be any other possible values of A1 and A2 that is going to give this result 0.75. Similarly, you can also see that this sample 0.6 is also linearly dependent on the past two samples 1 and 0.75, and that you can also do the similar calculation, and here you can find that if you assume this a1 okay equals to 1, you will get this a2 equals to minus 0.533, and similarly if you have this a2 equals to 1, then a1 will be equals to minus 0.15. So these are the two possible combinations of A1 and A2, which is able to generate this samples 0.75 and 0.6 by having the linear combination of their past two samples. So here in this case, I have just taken the order of predictor is equals to 2. And by just having this idea, you can see there is a possibility to generate these samples, okay, by having these values of A1, A2, and A2 and A1, okay. So the point is that you can understand here is that here I have just taken this value 0.75 to evaluate this A1 and A2. But the problem is that in the case of linear prediction, we actually don't have this value 0.75. The value which is having with us is only 0.5 and 1. And by just using this 2 and providing a certain values of A1 and A2, we have to generate this 0.75. So this is the problem of linear prediction, in which we have to find out these values of A1, A2. Okay, so these coefficients values we have to find out. So normally these coefficients are called as the linear predictor coefficients, right? So this linear these coefficients A1 and A2 are called as the prediction coefficients or linear predictor coefficients. Okay, and we have to evaluate this coefficients values. Okay, so now we have to move on to the concept of speech signal, okay, and then we have to understand how this linear prediction concept can be used in the case of speech signals, right? So this is a very general definition that I have shown, okay. A similar kind of concept we have to use in the case of speech signal, right? So now here you try to see this particular block diagram. This is the block diagram of the simplified model of digital speech signal production system. Okay. So here you can see that as the speech signal is broadly classified into the two categories. One is the voiced speech and another one is the unvoiced speech. So in the case of voiced speech, I have already discussed in my lectures that the excitation is going to be the impulse train generator, which will be a periodic in nature. And to generate this periodic impulse train, we have to apply the speech period as the input. Similarly, for the unvoiced speech, we have to use the random noise generator. Okay, so the amplitude of this means impulse train generator or impulses will be and noise generator will be governed by this particular multiplication factor G, right? So this G will going to decide the amplitude of those input signals. So now these input signals will go through the vocal tract. Okay, so normally this vocal tract functions is actually being modeled by the time varying digital filters. So this digital filter, whenever this excitation will go as the input to this digital time varying digital filters, then the output will be the speech sequences Sn. So this way your speech sequences Sn is going to be generated. So here we already know, we have already discussed these things before, okay. This time varying digital filters are actually related with the vocal tract parameters, and basically this vocal tract parameters we mean to say the area functions of the vocal tract, okay. So here is the general transfer function of a vocal tract filter, okay, in the Z domain. So it will be Sz upon Uz equals to G upon 1 minus summation over k equals to 1 to p ak z to the power minus k. So we know that this transfer function of the vocal tract filter will be an all pole filter, or all pole filter. Okay, it is just having the poles. Okay, we don't have any zeros. So now if you just cross multiply these things and if you take the inverse Z transform, you will be able to show this particular equation, which is Sn equals to sum over k equals to 1 to p ak Sn minus k plus g into un. So now if you further extend this summation, you can write this equation as n equals to a1 s into n minus 1 plus a2 as n minus 2 plus up to ap s into n minus p plus g into un. So here, as I said, that this a case denote you the filter coefficients. Okay, here we have this time varying digital filter So here this AK represents the coefficients of the digital filter, right? So here this AK means A1, A2 up to AP are the digital filter coefficients, and ultimately this digital filter coefficients are related with the vocal tract area functions. Okay, so here this P denotes you the number of uniform tube sections which is used in the lossless tube model. Okay, so as I said, I have already explained you that the vocal tract, the complete vocal tract, which is having its beginning from its glottis point, and it will be end up at the lip position. So from the glottis to lip position, the vocal tract will be divided into uniform tube cross sections. Okay, so the number of such uniform tube sections here in this case is P. Okay, so the number of P represents the number of uniform tube sections, right? So now, here you can see, because this is space sequence Sn which is being generated, okay, is actually a result of the past sequences, past sample values, which is being multiplied with the filter coefficients A1, A2, and up to AP, and then plus this particular generator, this particular excitation UN. Okay, so the problem is how to identify or how to uh, get these values of A1, A2 up to AP. Okay. The problem is how to get these values. So whenever, if you are recording any speech sequence, okay, whenever you are recording any speech sequence, and before that you just try to say this G is the gain parameter. And as I have already explained you, this G denotes you, or it is controlling the amplitude of voiced or unvoiced excitation. Okay, this is your G parameter, right? Which is called as the gain parameter. So here you try to again understand, because whenever you are recording any speech sequences, okay, if any speech sequence, if you are recording any voice, in that case you are going to get this random signals. Okay, obviously this random signal you are going to discretize by having the sampling, and therefore you are going to get the random samples of your speech signal, right? So whenever you're having only speech sequences, okay, we are just having the speech sequences, then in that case we don't have the information about this filter coefficients, right? So whenever you are recording, just you are having this left hand side, you don't have this right hand side coefficients, you don't have A1, A2, AP. Okay, these filter coefficients are not known. Okay, so the problem of the linear prediction is that how to find out these coefficients A1, A2, or filter coefficients up to AP by just having these P sequences Sn. Okay, so this is the problem of the linear prediction, in which we have to find out this filter coefficient by just having these P sequences Sn. Okay, so this is to try to understand. Okay, because by using this linear prediction concept, we have to find out the filter coefficients A1, A2 from the given speech sequence Sn, right? Because we don't have access to these values, right? Because once you are recording anything, you are just end up with just having these speech sequences Sn, right? So those samples will be available. Only the samples of essence will be available, right? The your sample values, right? Sample values will be available. After sampling, you are just going to get the sample value of your Sn. So from those samples, you have to predict this filter coefficients, right? So now just try to understand how this concept of linear prediction can be used for predicting or evaluating those filter coefficients that we have to understand. So now you try to see this particular system. So let us suppose we are having a system or a cascaded structure of certain delayed elements. So there are total such p number of delayed elements which are in sequence or which are in cascade. Okay, so if we pass this space sequence Sn, if we pass this space sequence Sn through such system, okay, then the signal which is going to be available at the output of the system, we are calling that sequence is equals to S cap n. Okay, so here you can write this S cap n equation. Okay, so this S cap n equation you can write is S cap n equals to sum over k equals to 1 to p, because it is the delayed element, so that delayed elements will give you alpha k into s into n minus k. Okay, so here if you expand this, this can be written as sk cap n equals to alpha 1 s into n minus 1 plus alpha 2 s n minus 2 plus dash 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 plus alpha p s into n minus p. So here you can easily see this. This equation represents you the predicted value of Sn. Okay, here we are just trying to predict this nth sample of Sn. Okay, based on past p samples, right? Based on past p samples. So we are just considering the past p samples, and by using those linear combination of those past p samples to predict the present sample n. Okay, so that's why we are calling this s cap n as the predicted signal of Sn. Okay, so now we have to consider, we have to find out the values of alpha 1, alpha 2 and up to alpha p. And here this alpha 1, alpha 2 will be called as the predictor coefficients. Okay, so here we are rather calling this as a digital filter coefficients. We are calling it as the predictor signal, predictor coefficients, right? So alpha 1, alpha 2 and alpha p's are the predictor coefficients. Here this P is the number of past samples used to predict the Sn, which is called as the prediction order, as I have already explained you before. Okay, so now you try to consider this system. Okay, how this predictor coefficients can be evaluated. For that, what we can design is we can have a system like this. Okay, so if you see this system, what we have is we are having this predictor. First of all, we are having this predictor. Okay, and this signal will pass through this predictor. The output of the predictor is this cap n, and then we are subtracting this s cap n, the predicted signal, from the present sample Sn, right? So this is the actual sample Sn, and if we are able to predict, if we are subtracting this to signal, we are going to get the prediction error En. So here we can write this prediction error En by writing this particular equation, right? So this prediction error is going to be Sn minus s cap n. So if you wish, you can rewrite this equation as equals to Sn minus sum over k equals to 1 to p alpha k s into n minus k. The same equation I have written over here. So I am just rewriting this equation here, right? So now the point is, if you remember how we had defined this Sn. Okay, so you can write this equation of Sn that we have already defined for the speech sequences. So this speech sequences can be written as k equals to 1 to p. Here the coefficient was ak s into n minus k plus g into un. Okay, so you remember here this ak denotes you the filter coefficient of the digital filter, right? And here this alpha k denotes you the predictor coefficients, right? So if you suppose that if we are having this alpha case equals to a case, if both the coefficients are having the same value, let us suppose this alpha k is equals to a k. In that case, this first term and third term will be cancelled out, and we are going to get this En equals to G into Un, right? So here, what we have to do is we have to actually find out the values of alpha k such that this error can be minimized. Okay, this error should be minimized. So basically, normally we are not just taking this error as En, but rather we have to reduce, or we have to minimize the mean square prediction error, right? So we have to actually calculate the alpha case based on this particular equation, but rather than just minimizing the error function En, what we have to do is we have to calculate, or we have to calculate the alpha k by minimization of the mean square prediction error. Okay, so I will just stop here, okay, in this lecture, and in my next lecture I will be discussing you how this mean square prediction error will be calculated, and how this minimization of the mean square prediction error will lead to will lead to give you the way so that we can be able to find out this alpha k values. Okay, so that we are going to look at in my next lecture. So I'll just stop here, and I will discuss the same topic in the next lecture. So thank you for watching this video. If you are having any doubt, let me know with your comments. Thank you.